2.5 kilos of a perfect gas is compressed reversibly and adiabatically to half its original volume, while the temperature rises from 125 Celsius to 250 Celsius. The work done on the gas is 225 kilojoules. Calculate the specific heats CV, Cp, and calculate the molar mass of the gas. So let's think, before we dive into any algebra, exactly what the question tells us. Okay, so we have 2.5 kilos of a perfect gas. And when we hear the words perfect gas, we should be immediately thinking of the following facts. Cp is constant. Cv is also constant. Therefore, the ratio of Cv and Cp is also constant, gamma. And the difference between Cp and Cv, which is the gas constant, will also be a constant. Furthermore, we know that for a perfect gas, the internal energy, the specific internal energy, and the specific enthalpy are a function of temperature only. So we use letters small u and small h, and these are a function of temperature. Okay? And of course we can also use the ideal gas law. The next part is compressed reversibly and adiabatically. And what does that tell us? If something's reversible and adiabatic, it's isentropic. And if it's an isentropic compression, we can use the isentropic relations. For example, we know that here we're told the change in temperature and the change in volume. So let's write the isentropic relation for temperature and volume, which is that Tv to the gamma minus 1 is a constant. Okay, so they tell us also what the work done is on the gas. Now, if we have the amount of work done, we can use the first law perhaps to say something about the change in internal energy, U. So let's just think through how we're going to answer the question. It's asking us for Cv and Cp and the molar mass of the gas. So maybe pause the video and see if you, based on what the question's told us, you can formulate a way to first of all calculate Cv. Okay, so in order to calculate Cv, we need to know what the definition of Cv is. So it's the constant volume heat capacity, but really it's defined, and of course this is not a constant volume process, but the real definition of Cv is not strictly in terms of a constant volume process. It's the partial derivative of the specific internal energy with respect to temperature at constant volume. Where this is a specific constant volume heat capacity. However, we know that U is only a function of temperature for this gas, perfect gas, so we can actually drop the constant volume condition here. And so for an ideal gas, or a perfect gas, indeed for a semi-perfect gas, this is true, even for a non-constant volume process. Therefore, if we know what delta U is and we know what delta T is, we can calculate Cv. So now we need to find out what delta U is, and since we know what the work on the system is, we can use the first law in order to obtain the change in delta U. So the first law says that delta U, where this is a big U for the total internal energy, is equal to the heat added to the system minus the work done by the system. And we need to be very careful about our sign convention with the first law. And in the question we're told that that the work done on the gas is 225 kilojoules. Therefore, the work done by the gas is the reverse of that, is the negative value of that. So the work done by the gas is equal to minus 225 kilojoules. And since the process is adiabatic, what's the value of Q? It will be 0. So delta U is going to be minus W or plus 225. Now, since we know what delta U is, we can calculate what CV is. It's equal to delta U over delta T, and that's okay. Here we need to be a bit careful. So here this is a big U for the change in internal energy. Here, if we want a specific heat capacity, this is per kilo. And in order for it to be kilo, this needs to be the specific internal energy, the small u. And to get small u from big U, we need to divide by the mass, which was 2.5 kilos. So here we need 225 kilojoules, so times 10 to the 3 over 2.5 kilos divided by delta T. And we've gone from 125 to 250 Celsius, so that's a difference of 125 Celsius or Kelvin. And if we put the numbers in there, the value we will get is 720. The units here are joules, because we will be working in joules per kilogram here. And now that's per kilogram Kelvin. The next thing we were asked to answer is to find the heat capacity. Now, going back to the constant pressure heat capacity, going back to the things that we've deduced from the question rubric up here, we know that Cp, Cv, gamma and R are all constant, and that for an isentropic process we can apply this relationship between changes in temperature and changes in volume. Now in the question we're told both the change in temperature and the change in volume, so this is going to allow us to deduce what gamma is, and then we need to remember that gamma is equal to the ratio of heat capacities, and that allows us to calculate Cp. So now that you've had that hint, I suggest you pause the video and try and work through that. Okay, so we have an isentropic process here. So we know that the ratio of volumes, or let's first of all just write that gamma is equal to Cp over Cv. And this relationship is going to allow us, since we know what Cv is and we're about to find out what gamma is from this relationship, it will allow us to get Cp. The isentropic relationship tells us that the ratio of volumes power of gamma minus 1, where this is volume 2 over volume 1, is equal to the ratio of temperatures, where this is temperature 1 over temperature 2. Now we know that volume 2 is half volume 1. We also know that temperature 1 is 125 Celsius, temperature 2 is 250 Celsius. Okay, so this volume ratio is a half. And in order to get gamma minus 1, we're going to take the logarithm of that. And that's equal to the logarithm of this temperature ratio. Now we need to be a little bit careful here. because we're given the temperatures in Celsius, but this ratio applies in terms of absolute temperature. So we need to convert from Celsius to Kelvin. So the initial temperature was 125 Celsius. We need to add on an offset to take us into Kelvin. Now we need to put this into our calculator carefully, and I'm not going to do that here in front of you, but the value that we get out is 1.390 and some more decimal points. Therefore, we can evaluate Cp is equal to 1.390 times the value of Cv, which was 720 joules per kilogram Kelvin. This gives us 1003, and if we keep all the decimal points throughout the calculation, we can write that to a lot of significant figures. Joules per kilogram Kelvin. Okay, so that's done. Right, the last part of the question, molar mass of the gas. How are we going to get that? Okay, well, what do we know? We know Cp, Cv, gamma. Therefore, we also know the value R, the molar heat capacity. And that's equal to Cp minus Cv. So R is equal to Cp minus Cv. In addition, we know, or may recall from last year, that the value of R for this particular gas is equal to the universal gas constant over the mean molecular weight, m. And it's the mean molar mass, or the mean molecular weight, that we're trying to find here. So m is equal to R naught over Cp minus Cv. Now let's just put the values in there. Value of the universal gas constant, if you look in your data book, it's in there. 8.314 joules per mole per Kelvin. And we want to divide that by Cp minus Cv, which is 1003.7 minus 720 joules per kilogram per Kelvin. Which is equal to 0.0293 kilograms per mole. Or it's more common, I guess, to write it as 29.3 kilograms per kilomole, which is roughly the value for air, which is a mixture of nitrogen with molecular weight 28 and oxygen with molecular weight 32. Okay, well, I think we should just summarize that the trick to solving this question is really to study very carefully what's in the rubric of the question and to glean all the necessary information. Things that may trip people up is that the definition of Cv doesn't only apply to a constant volume process when we have an ideal gas. We can use it for this compression process by knowing that Cv is defined as the partial derivative of internal energy with respect to temperature. So that's a more general definition than saying it's a change in energy at constant volume.